How temperature changes affect ice phenology for lakes in Canada by Faith Roy, Samantha Spearing, and Coleson Thurston. The changing of ice. Across Canada, thousands of freshwater lakes freeze every winter, and this ice cover is a big part of our winter environment. When we look at ice, or ice phenology in our case, we're really looking at when lakes freeze up, how the ice develops during winter, and when it melts in the spring. These timing changes might seem small, but they're actually really useful for understanding how our climate is changing. Things like air temperature, wind, snow cover, and the size of lake all affect how ice forms and melts. These patterns help us see bigger environmental trends. Why it matters. Ice phenology matters because ice affects a lot of physical and ecological processes. If the ice forms later or melts earlier than usual, it changes how the lake mixes, how oxygen moves around, and how nutrients cycle. These shifts impact the overall functioning of the lake. Lake ice is also highly sensitive to temperature changes, so when the freeze up or the melting dates start to move, it's usually a sign of warming conditions. Studies, including long term research, show that many lakes are warming, experience shorter ice seasons, or sometimes not freezing completely. These changes affect species too. Cold and under ice organisms depend on long, stable winters, while warmer water species may start expanding. Earlier melt can also increases the chances of eutrophication or harmful algal blooms, which can affect ecosystems' health overall. The study of ice. To study all of this, scientists used a mix of satellite monitoring and in-lake instruments. SAR satellites, like RadarSat-2, are especially useful because they can collect data through clouds and even in total darkness, which is perfect for winter conditions in more rural areas. Researchers also use temperature sensors and thermistor-based sensors inside lakes to measure how heat moves through the water column and how that influences ice formation. Autonomous devices like Simba units are used in more extreme or remote locations to track snow depth, ice thickness, and temperature without constant field work. Some studies have shown how deeper lakes freeze differently than shallower ones. For example, deeper lakes may freeze later but build ice faster because they hold colder water underneath, while shallow lakes may freeze earlier but more slowly due to warmer bottom sediments. By combining satellite data, temperature measurements, and long term observations, scientists can get a much clearer understanding of how lake ice is changing and what that means for ecosystems and our overall climate.
What are the trends? Canadian lakes are showing clear climate driven changes. Freeze up is happening later each fall, while breakup occurs earlier in spring. This shortens the total ice season significantly. We're also seeing rising lake temperatures, which delays ice formation and accelerates melting. In warmer years, some lakes don't fully freeze at all. When ice does form, it's often thinner and more unstable due to fluctuating winter temperatures. One important detail: lake morphology matters. Deeper lakes freeze later, but build ice quickly once frozen, while shallow lakes warm faster and are more sensitive to temperature changes. Overall, these changes align with long-term climate warming across Canadian freshwater systems. The shifts in or ecological impacts. The shifts in ice patterns have serious ecological consequences. Earlier spring melting changes how oxygen and nutrients mix throughout the lake, affecting water quality and habitat. Delayed freeze-up is concerning because nutrients stay near the surface longer, increasing the risk of harmful algal blooms that stress aquatic organisms. Cold water species like lake trout are especially vulnerable. Warmer temperatures reduce their habitat while giving warm water and invasive species room to expand. We also see timing mismatches. When seasonal cues shift, predators and prey fall out of sync, disrupting food webs. Finally, thinner ice means less oxygen accumulates underneath, raising the risk of winter fish kills. Societal impacts. These changes directly affect northern indigenous communities. Thinner, unstable ice increases risks on ice roads that many communities depend on for safe winter travel and mobility. Traditional activities like hunting, trapping, and winter fishing depend on reliable ice access. Late freeze-up and early melt restrict these activities, affecting both food security and cultural practices. Winter gatherings on ice events and recreational activities like ice fishing and snowmobiling face shorter seasons and disrupted traditions. For many communities, predictable ice is essential. Climate-driven shifts create widespread challenges for safety, culture, and livelihood.
Now, for gaps in current research. Our group has identified four major gaps that hinder our understanding of these changes. First is the short term focus. Climate change occurs over decades, yet most studies only look at brief snapshots in time, missing the bigger picture. Second is geographic limitations. Science tends to focus on single, easily accessible lakes, so we lack a cohesive national view of how ice is changing across Canada's vast and diverse geography. Third, we face equipment constraints. Current autonomous sensors frequently fail in harsh northern winters, leaving us with data blind spots. Finally, this leads to fragmented data. Without standardized reporting across the country, it is incredibly difficult to build the accurate models needed to predict future trends. The looking ahead section of our research emphasizes a shift from simple observation to complex understanding. We need a holistic approach. It's not just about when ice melts, but how that melt interacts with water chemistry, lake depth, and surrounding geography. Future research must treat the lake as a complete system. This allows for better impact assessment. If we can understand the physical changes in the ice, we can predict the biological consequences, such as oxygen depletion affecting fish populations. The goal is to move from recording history to predicting future ecosystems. To conclude, the data from the last 20 years is clear. Canadian lakes are freezing later in the fall and breaking up earlier in the winter. Also, winter ice roads are the lifeline for northern communities, transporting food, fuel, and supplies. As ice becomes unstable, these socioeconomic risks skyrocket, threatening both safety and traditional hunting practices. Biologically, these warmer waters are now favoring invasive species over native cold water fish. Our strategy moving forward is threefold. One, we must extend satellite monitoring to create a continuous 30-year dataset for better statistical accuracy. Two, we need to deploy robust autonomous sensors to get ground data from diverse ecozones. Three, we must integrate this data into advanced climate models to predict hydrological changes before they become emergencies. Now, our references.